In your algebra way back in junior high school, you learned how to determine the equation of the line using different methods, namely two-point form, point-slope form, slope-intercept form, and etc. However, determining the equation of a line that is tangent to a given curve at a particular point requires the use of limits. Finding the equation of a tangent line is the frontliner in the introduction to derivatives. In Lesson 1, we will define tangent line to the graph of a function at a given point. Draw tangent line to the graph of the function at a given point and formulate the slope-intercept form equation of the tangent line of a function at a given point. We will now formally define what is tangent line in calculus. Let C be the graph of the continuous function y equals f of x and P be a point on C. A second line to y equals f of x through P is any line connecting P and another point Q on C. We select any point Q on the graph and we connect point P and Q with a line. This line segment PQ is a second line of y equals f of x through P. The tangent line to y equals f of x at P is the limiting position of all second lines PQ as Q approaches P. Note that second line touches the graph in 2 points P and Q. Observe the illustration on the right. If we move the point Q closer and closer to P, represented by that series of points in between P and Q, we can come up with a line that only touches the graph at P, because at this point, P is the same as Q. Such line is called tangent line. It shows that the tangent line is the limiting position of all second lines at a certain point on the graph, both from the left and the right of such point. Whenever the graph is smooth or there are no sharp corners, the tangent line at the peak A and trough B are always horizontal. Peak is the highest point of the periodic graph and trough is the lowest point. How about if we have a point C right at the middle of A and B? The tangent line here is of course not horizontal nor vertical, but diagonal one falling to the right. For a straight line, the tangent line to another line at any point is the line itself. In the illustration, the tangent line to line L at P is line L itself. This debunks the idea that a tangent line touches the graph at only one point. In calculus, we have to follow how tangent line is defined. In this graph, the tangent line at P is a vertical line. In some cases, some graphs have no tangent line, or in other words, the tangent line does not exist. There are only two cases when this happens. The case when the function is not continuous at x sub 0. It is clear from the definition of the tangent line that the function must be continuous. Second, the case when the function has a sharp corner or cusp at P. This case produces different limiting position of the second line PQ, depending on whether Q is to the left or to the right of P. If these are the graphs of the function with corner at P and cusp at P, tangent lines do not exist. After validating if the tangent line does really exist or not, the endeavor in calculus will not stop there. We will go beyond and get the equation of that line. There are two steps to follow. First, we need to compute the slope. We have the formula m equals y sub 2 minus y sub 1 all over x sub 2 minus x sub 1. We will now modify this formula to include the definition of the tangent line and the coordinate of the point P, x sub 0, y sub 0. So we have the limit of y minus y sub 0 over x minus x sub 0 as x approaches x sub 0, because tangent line per definition is the limiting position. and we change y sub 2 and the x sub 2 by y and x respectively, and the y sub 1 is our y sub 0 and the x sub 1 is the x sub 0. And since y equals f of x and y sub 0 equals f of x sub 0, we will substitute those equivalents. So our slope now becomes the limit of f of x minus f of x sub 0 all over x minus x sub 0 as x approaches x sub 0. So we will be using this formula in computing the slope of the tangent line. If you have now the value of the slope and the coordinate of the point P, then we will substitute those values to this equation. Y minus y sub 0 equals m times x minus x sub 0. For this example, find the equation of the tangent line to f of x equals x squared at x equals 2. The given is x equals 2, and this is equivalent to our x sub 0. To get the f of x sub 0, we will substitute this 2 to this equation, x squared. So the x sub 0 is 2, so you have 2 squared, that is equal to 4. Thus, the coordinate x sub 0 and f of x sub 0 is equal to 2, 4. This one and that one. To solve for the slope, we have that formula. The f of x is equal to x squared, so we have x squared, minus the f of x sub 0 is this one, that is equal to 4. So for the numerator, we have x squared minus 4. And for the denominator, copy x minus the x sub 0, the given is 2. So you have x minus 2. After that, we will apply the factoring in the numerator. The factor of x squared minus 4 is x plus 2 and x minus 2. We can cancel x minus 2 as the common factor, so the answer now is x plus 2. The limit of this ratio is equal to x plus 2, and that is now equal to the limit of x plus 2 as x approaches 2. Y approaches 2 because our x sub 0 is positive 2. So just substitute the value of the x in x plus 2, so you have 4. So our slope here is positive 4. Since we have now the value of the slope and the coordinate, so we can use this equation, the point slope form. So just do the substitution for our y sub 0, that is 4. The slope is 4. X minus the x sub 0 is 2. So that is the equation of the line in the point slope form. We can still modify this equation. Just simplify the right side, so 4 times x is 4x, 4 times negative 2 is negative 8. Retain y on the left, so you have the additive inverse of negative 4, that is positive 4. So our slope-intercept form of the tangent line is y equals 4x minus 4. Now that you have already an idea of the tangent line, we will now proceed to the definition of the derivative. In this section, we will define derivative and solve for the derivative of a function at a given number. Let f be a function defined on an open interval I subset of the real number system, and let x sub 0 element of that open interval. The derivative of f at x sub 0 is defined to be f prime of x sub 0 is the limit of f of x minus f of x sub 0 over x minus x sub 0 as x approaches x sub 0, if it exists. Another notation for derivatives are denoted by the following on the right. If you will encounter them in the next lesson, those symbols are for the derivative of f of x, or the derivative of y with respect to x. Let's proceed to the examples. Find the derivative of the function at 1 of the function f of x equals 3x minus 1. From this given, this one represents our x sub 0. And since we need to compute the f of x sub 0, then we will use this value in this function to get the f of x sub 0. The function is f of x equals 3x minus 1. And for our f of x sub 0, so we have f of 1. Substitute 3 times 1 minus 1, and that is equal to 2. So the x sub 0 is positive 1, and the f of x sub 0 is positive 2. Then we will substitute those values to the definition of the derivative. To solve for the derivative of the function at 1, our f of x is 3x minus 1. So you have this minus our f of x sub 0. F of x sub 0 is positive 2. So that is positive 2 all over copy x minus the x sub 0 is 1. Simplify, that becomes 3x minus 3 over x minus 1. We can factor the common in the numerator. So the common is 3. 3x divided by 3 is x. And the negative 3 divided by 3 is negative 1 all over x minus 1. Since we have the same factor, we can cancel out the x minus 1. Therefore, we have only positive 3 as the simplified form of this expression. So, the derivative now becomes the limit of 3 as x approaches 1. And the limit of 3 as x approaches 1 is positive 3. For the second example, compute the first derivative of 1 of the function f of x equals 2x squared plus 4. For the given, we have x sub 0 is positive 1. And to solve for f of x sub 0, so we have this function. We will replace x sub 0 by 1. And by substitution, we have positive 6. To solve for the derivative of the function at 1, so we will use this formula. F of x is 2x squared plus 4 minus f of x sub 0 is positive 6 all over x minus the x sub 0 is 1. We will now simplify this ratio. For the numerator, this is equal to 2x squared minus 2 over x minus 1. Factoring the common, so we have 2 times x squared minus 1. And since x squared minus 1 is still factorable, then we will factor this into x plus 1 and x minus 1 all over x minus 1. We can cancel x minus 1. So the remainder now is 2 times x plus 1. After simplifying this, we have the limit of 2 times x plus 1 as x approaches 1. Just substitute x equals 1. So you have 2 times 1 plus 1 and that is equal to 4. That means to say that the derivative of the function at x equals 1 is positive 4. There is another method to get the derivative of the function at a certain number x, and that is the alternative definition of the derivative. In this lesson, we will solve for the derivative of a function at a given number using the alternative definition of the derivative. Let f be a function defined on an open interval I subset of real number, and let x sub 0 element of I. The derivative of f at x sub 0 is defined as f prime of x equals the limit of f of x plus h minus f of x over h as h approaches 0. So the only difference here of the first definition is that we are not anymore using x sub 0. And here we have only x and we add some variable h. Let's proceed now to the example. Find the derivative of the function at x equals 1 of the function f of x equals 3 minus 14x. From this formula, we will substitute the value of x, which is positive 1. So that becomes f prime of 1. And replace all the values of x by 1. So you have f of 1 plus h minus f of 1. Since we have f of 1 plus h and f of 1, then we need to solve these values independently. And for the denominator, we have h as h approaches 0. This part, this is a constant. To solve for f of 1, just use the function, replace x by 1, so we have negative 11. Let's proceed now for the f of 1 plus h. To solve for f of 1 plus h, we will just simply substitute the entire value of x by 1 plus h. So from the function, we have 3 minus 14, change this x by 1 plus h. After that, simplify, so your negative 14 times 1 is negative 14, and negative 14 times positive h is negative 14h. And combine the constant, so you have negative 11 minus 14h. Note that our f of 1 here is negative 11 and our f of 1 plus h is negative 11 minus 14h. And from this equation, the f prime of 1 is the limit of f of 1 plus h minus f of 1 over h as h approaches 0. So just substitute f of 1 plus h, this one. So you have negative 11 minus 14. Your f of 1 is negative 11. So you have minus negative 11 over h. We will simplify first this ratio. The numerator is the same as negative 11 minus 14h. This is negative and negative. That becomes positive 11. Negative 11 and positive 11 can be cancelled out. So we have now negative 14h over h. Then we can still cancel h and h. So the simplified form now is negative 14. Since the simplified form of this ratio is negative 14, so we have the limit of negative 14 as h approaches 0, and that is equal to negative 14. The derivative of the function at x equals 1 is negative 14. A while ago, we have shown that the derivative of f of x equals 2x squared plus 4 if x equals 1 is 4. I will present here how to use the alternative definition of the derivative to get the value of 4. So this is our equation, and to solve for f of 1, by substitution we have positive 6. And for our f of 1 plus h, just substitute the x by 1 plus h. So we have this 2 times 1 plus h squared plus 4. Then square this binomial. Square the first term, we have 1. Twice the product of the first and second, 2h. Square the last term, h squared, plus 4. Then, distribute, 2 times 1 is 2. 2 times 2h is 4h. 2 times h squared is 2h squared, plus 4. Rearrange the order, so you have 2h squared plus 4h plus 6. That is for the value of our f of 1 plus h. Then we will substitute those values to our equation for this one. So you have 2h squared plus 4h plus 6. And for our f of 1 is positive 6. Simplifying this, so we have 2h squared plus 4h plus 6 minus 6. We can cancel the positive 6 and the negative 6. So the remainder now is 2h squared plus 4h over h. The numerator has common factor of 2h. So factor out. So that becomes 2h and h plus 2 over h. We still have common factor of h. So we can cancel h and h. So we have now 2 times h plus 2. The simplified form of this ratio is 2 times h plus 2. Substitute h equals 0. So you have 2 times 0 plus 2, and that is equal to positive 4.